The analysis meeting was cancelled today, so this is the complementary video to my question. I will try to make it as brief as possible. So I won't go through my whole presentation, but I will just start off with this. So if you recall from last time, this is my phase space figure. We have the xi parameter on x and the neodymium amplitude parameter, which is proportional to the inverse of half-life on the y-axis. And we've obtained these contours, the light grey ones are the ones that are most interesting to us at the moment. They are the systematic and statistical contours. So we have converted this into a probability space, and I should have brought this up before, but it's also in my presentation, I believe. It would be good to show the method used to do this. I'll find it from my previous presentation, I think. So I think it should be in this one. Yes. Okay, so taken from this source, this statistics lecture, this is how we converted from our chi-square values to the probability space. So we just took the exponential of the chi-square value, the negative chi-square value divided by 2, and then normalized using this second point here. And then finally, we will use this in a second. This is to marginalize the probability distribution. So just to take essentially what Root calls a profile. Okay, so this is what we've done to create this probability space. Now, what we're interested in doing is marginalizing this, for example, for the half-life parameter. So to create this particular figure here. And the way this is done is to use these figures. So firstly, what I do is find do the marginalization process. So convert this 2D probability space into a 1D probability space. So just using that final equation that I showed you a minute ago, this one here. So using this to sum all the probabilities along one dimension and then convert that into a single dimension probability space. Now this looks quite Gaussian, but it's not, and this is what the question really relates to. So the most probable value is the peak, which is about 1.19. So what I want it to do is, previously I've actually shown this figure, which is a one-sided limit, which is not really the correct thing to be doing here. We should find a two-sided limit. And the way that's done is to firstly take the peak value and integrate in both directions. So that's what these figures are here. So we have the cumulative probability distributions, the low and the high end. So I'll flip them around. So the low one, you can see the parameter varies from 0.19, which is the peak, and as you move away from 0.9, you go to more negative values and the integral increases and it goes up to a value of a bit above 0.48. And then on the other side, if you integrate from 0.19 all the way up to 1.45, which is the limit of the bounds of this space, then you get a probability that is a bit above 0.5. So let me just prove that to you. It is about 0.514. So I can unzoom that. Now the question here relates to the fact that these integrals, these areas are not equal. So the question is, if I were to find a 99% confidence level, what you would usually do is to do a two-sided limit. You would take the peak of this distribution here and integrate until you find 0.99 divided by 2. Now, we can't do that on this side because 0.99 divided by 2 is more than the area under the lower bound of this figure. And on this side, the 0.99 over 2, well, actually, let's just say we were to find a 100% confidence level limit. Now, obviously, you would expect that to be somewhere out at infinity with a true, if this was a true distribution, but it's cut off. It has a limit to the space. So because it's normalized such that the area is 1, we should be able to integrate and find 100% probability confidence level limit. So what we would do is go from the peak and integrate until we found 50%, which is a half of 100%. And obviously on this side, if we integrate to 50%, we come to here, and there's still more probability area beyond the limit where we approach 0.5 of the area. So hopefully that makes sense. There's a possible resolution that I've proposed, and that is to, if I can find the document, I called it a Bayes limit, but it's not actually Bayes' theorem at all. It's a it is a what would you describe this as? It's a conditional probability. So as I just described, we can, on one side, if we do an integral like this where x0 is the peak, we can't obtain the confidence level limit we're looking for. Here I've used 90% as an example. We can actually obtain 90% on these figures because half of 90% is 45, and that would be about there. So on one side, if we went to go to a high enough significance level, we wouldn't be able to find a limit. We wouldn't be able to solve for x0 we wouldn't be able to solve for x, which would go here, because if we go out to infinity, we can't reach that confidence level limit. And similarly, in the other direction, if we integrate to infinity, we would obtain more than 100%, which doesn't make any sense. So we could redefine these limits, and this is my proposed solution, but I don't know if it has a statistically meaningful interpretation or whether there's a better way. We could redefine our probability, so we could say that A1 is the area on one side, A2 is the area on the other side, and we could find 90% of A1 or A2 to find a 90% confidence level limit. I don't know if this is valid though, and that's the question I want to pose to the analysis group. So this is a bit like finding a 90% limit given a condition. So given that x is less than the peak, we find the 90% probability given this, and I think that's just, I think it's just multiply. Somebody else will, maybe this is not the best notation, maybe this is not the correct way to write what I'm trying to describe. My point being that you would calculate this thing here. So if I just zoom in, if we wanted to find a 90% confidence level, the proposal would be to first integrate to infinity to find the total area on one side from the peak being this x0, and then solve this equation. So we would find a half of the confidence level, but multiplied by the area we have. So we would find this. So we would go to a value of x that solves this equation. And similarly, we could do it for the positive side as well, where we had from x0 to infinity. So that's the end of the question, really. To understand how these figures are made, perhaps I can show these figures. So this would be the cumulative. I'll put it here. This would be the cumulative distribution of this probability distribution here. Same limits, but integrating from 0. So that's what you would normally think of as a cumulative distribution. The difference with these ones is we're integrating from the peak. And then to find the confidence level, if you take the y and x inverted version of this, the inverse, if you want to find a confidence level of 90%, you'd have to go to here. That's 90% there. And you just go up and read off what the limit is. So a one-sided limit for this distribution, 90% confidence level, gives us about 1.25 maybe. What did I have on my presentation? I said 90% was, okay, 1.11 apparently, from minus 0.1 to 0.11. Oh, that one was for Xi, actually. Not Half-Life. These figures I'm showing here are for Half-Life. So for Half-Life, it's obviously different. It's doesn't matter that much, but it's a bit above 1.25. Okay, fine. So the only other comment I have is because this space is bounded, I don't know. There's one possible solution, another possible solution, and that is to cut off a small piece of the space such that this thing then is symmetrical. I don't know. That's very fiddly. That's not. I wouldn't like to do that so much, because this thing is an array of 301 by 301 points that sample the chi-square value, and it's not guaranteed that well, it obviously won't be the case. If I slice off 1 or 2 rows, it's not guaranteed that I will end up with something symmetrical. It will just become closer to being symmetrical, which means that then I can integrate to higher and higher confidence level limits. So at the moment I can integrate this and find 90%, because I have to go to 0.45. I can go to 95%, but then my limits become very, very asymmetrical. So I'll just show you them. They're here on this let me just increase the font size. Okay, so the 1 sigma half-life limit, so the central value is about 1.19, and I obtain plus or minus 0.067, and that's about symmetrical. And then if I go to 90%, so the difference here is 1 digit in, it's the thousandths digit, right? That's the first digit that's different. This one is the same, actually. Oh no, it's not. Sorry, the 100th digit is different in this case. So for 90%, where I go to 0.45, the limits become more asymmetrical, and then this digit is now changing by 3 for the 95% confidence level limit. And so this asymmetry is artificial, right? Because when I'm calculating these, I'm not normalizing the area on either side. So I'm integrating to 90% of A1 or A2. I'm just integrating to 90%, 95%, 99% of the total area. So if you try to go to 99%, this one makes no sense. The reason being, let's look where these limits lie. Right, so for or 99% the high limit 1.148. So that's this one, 1.14. So it's in here. Sorry, no, it's not. 1.1 sorry, plus 0.14. So we have to add 1.19 plus 1.148. Let me just, I'm not going to do that in my head. I'm going to do it using Python. So 1.19 plus 0.148. So it's 1.338 apparently. So 1.338 is in here. 1.338. So we obtain a limit of 0.494. So I unzoom again. So 0.4, what did I say? 0.494 was it? Yeah, could have been. So up here somewhere. The point being that I can go all the way to 100% and not reach this limit here. And for the other one, it's even crazier. So minus 0.49, so about minus 0.5, so 1.19 minus 0.5. So we've got to go from here to minus 0.5, so that's minus 0.1, 2, 3, 4, 5. So it's like way out here beyond where the data ends, right? Because integrating, that's the wrong marginal one. Where's my marginal for half-life? There it is. So integrating this down here, you get to 0.95 and there's no longer any more data, so you hit a limit. And my evaluation has said, well, the answer is all the way out here. And the reason that is because I think it's interpolating. So it's interpolated from here all the way out to here, which is clearly, it doesn't make any sense, right? So that's it. I'll end it here. And I'll do the full presentation next week. But obviously, to speed things up, it'd be really great to get some feedback on this before then. So thanks very much.